Hello, everybody. My name is Shubhaditya. Today, I'll be presenting the paper titled Generative Multiplane Images, Making a 2D GAN 3D Aware. So the schedule is like this. First of all, I'll be explaining a brief overview of what the topic is. Then the background based on which the authors have written this paper. Then an important concept which authors have mentioned here, which is the generative multiplane images. And finally, I'll end with the experiments. So first, the overview. Before going deep into the actual content of the paper, I'll just briefly explain what generative adversarial networks are. So as you see, there is a small pictorial representation here. So basically, two neural networks contest each other. So there is this generator, and then there is this discriminator. So generator generates candidates while the discriminator evaluates them. The generative network's training objective is to fool the discriminator basically by producing novel candidates that the discriminator thinks are part of the true data. So these are the real images, and then there is a discriminator. Generator needs to generate exact copies of the real image, not exact copies, the copies which the images which closely resemble to the real images so that it can fool the discriminator. So this is a basic structure of the GANs, and they are very successful at sampling novel images where the output space of the generator is identical to the training data set is just the real images. Now, recent research focus has been to develop 3D aware GANs for generating novel outputs that differ from the available training data. So it's exact opposite what I just explained. So recent research focus is basically based on that. Now, prior work typically combines 3D aware inductive biases, such as a 3D voxel grid or an implicit representation. Just a point to note, no multi-view images or 3D geometry are used to supervise the training of these so-called 3D aware GANs. The challenges which are being faced in this kind of research is one, that the these processes are extremely memory intensive and they are computationally demanding. And often the learned results are not transferable from the 2D GANs directly to make the GAN 3D aware. So let us move forward. So far we have seen 3D GANs based on the explained ideas are expensive computationally. So to circumvent this problem, the authors have claimed, rather they have demonstrated that multiplane images, a concept of multiplane images can be used as a scene representation for unconditioned 3D aware generative models. So what is the basic idea behind this? So the authors develop a new generator branch for an already developed model, which is a style GAN V2, which is very popular, which yields a set of fronto-parallel alpha maps in the spirit similar to the multiplane images. Now, once the alpha maps are created, they combine the alpha maps with single standard image output of the style GAN V2 in an end-to-end differentiable multiplane style rendering. So just by doing this, the authors obtain a 3D aware generation from different views while guaranteeing view consistency. The only necessary conditions for this is that the alpha map prediction of any plane in the MPI is conditioned on the plane's depth, because this is extremely important in order for the GAN to be 3D aware, because it has to have a depth perception. And the discriminator is conditioned on the camera poses as well. Now, so far, we have known that the authors claim that the MPI-based scene representation for these problems, MPI-based scene representation circumvents these problems, which we have talked about. Now, what we are going to see next is a brief background for the methods that are developed for classical and neural scene rendering, as well as 3D generative models from 2D data. So one of the quite popular and basic methods is image-based rendering. So these are well studied for scene rendering. Even though multiplane images and the IBR methods like NURFs, neural radiance fields, have a common goal of extracting a volumetric representation um, um, of the observed scene given a set of images, there are certain differences which which stand out, in which MPIs basically stand out. So IBRs use continuous spatial representation, whereas MPIs use discrete spatial representation. IBRs focus on reconstructing a scene representation from a set of images, but MPIs are unconditionally generative, and never seen before scenes can be synthesized without requiring any other information. And then IBRs use multiple viewpoints of a single scene for highly accurate reconstruction, whereas MPIs use a collection of single view images from different scenes during the training. So additionally, there are other methods also which have been developed. Some of them are early approaches used these voxel-based representations, but the voxel representation is quite prohibitive in a sense that while scaling to higher resolutions, it has extremely high memory footprint. Then to circumvent this, low-res rendering and 2D CNN upsampling was used, but it leads to view inconsistency. Then there were NURFs, which we just talked about, the image-based rendering methods, but they are quite costly. The querying and sampling operations limit the training efficiency and the image resolutions. So to generate higher resolution images, e.g. 3D, style NURF, SIPs, 3D volume GAN, and style SDF, and etc. These methods have also been developed. The only difference which the authors point out that their method has from these kind of methods is the choice of scene representation, where the authors use MPI-based type representations. So far, we have seen that the method is built on the StyleGAN v2 model. It makes sense to briefly go through what the internal structure of the StyleGAN v2 architecture is. So it generates a square 2D image, C, let's say, by upsampling and accumulating intermediate GAN generation results. So we have CH is the GAN image generation at resolution H, and C tilde H is the residual. So this residual is computed by convolving the feature with a single convolutional layer. This feature is in turn generated by a synthesis network, which takes in a style embedding, and style embedding is in turn generated by a mapping network, which takes in the latent variable. So we need to keep in mind all these networks, because these are the parameters, these are the models which will be important for model training at the end. Now, we have briefly seen the model definition of the StyleGAN v2. The future alpha branch model will also follow the same lines. So first of all, we go through the generative multiplane images, what the generative multiplane images are. So the general idea is like this. We can segment this big diagram into 3 different blocks. One is the generator block, next is the renderer, and then the discriminator. So this classical generator of the StyleGAN v2 is modified by adding an alpha branch. We'll look into what alpha branch is in coming slides, and incorporates a simple and efficient alpha composition rendering. The alpha branch produces alpha maps, and these alpha rendering platforms transforms generated alpha maps and image into a target view. So like IV target is the final view which is generated using a user given pose, which is camera pose V target. And once this is done, then the 3D awareness is achieved by including a pose conditioning on the discriminator. So let us look into what the alpha branch is. That is the first block, which we just talked about. So alpha branch, the objective of the alpha branch is given input latent code, it synthesizes a multiplane inspired representation. So what is a multiplane? Multiplane image is a set of tuples, which is Ci alpha I and Di for L frontoparallel planes. So I is from 1 to L. So the Ci is basically the color texture of the ith plane. Alpha I is the alpha, and D are the alpha maps and the depth of the corresponding plane. So D is the distance from the camera. As a significant simplification which the authors have used, they choose the same color throughout all the different planes, same color texture throughout all the different planes. So we do not have Ci's anymore. We just have one C. So the task of the generator now has been reduced from predicting an entire multiplane image representation to predicting just a single color image and a set of alpha planes. So as you can see through this, there is a feature, then the feature for each alpha i's, and then this is convolved and then upsampled and accumulated in order to construct an alpha map for a plane I. So the calculation, the computation of the alpha i's go through the similar goes on the similar lines of the style GAN V2 design, which we just talked about. Here also we have the same upsampling and accumulation. The residual is calculated with the help of this F2 alpha network. So it operates on each and every frame individually. And for each and every feature, the feature alpha I is calculated based on this formula, where mu and sigma are the mean and the standard deviations. There is a parameter called H alpha, which is taken to be less than H to reduce the memory usage. And authors argue that in the real world data, this doesn't make any difference. So now we have already seen the first block. Now for the second block and the third block, we come for differentiable rendering and the post conditioning. So differentiable rendering is just a warping step. It transforms the representation which we have already received from the generator, and it transforms it from its canonical pose to the target pose. And a compositing step combines the planes into the desired image. Now, once the second block is complete, that means the desired image is obtained. We need to do post conditioning on the discriminator. So this camera post conditioning of the discriminator is essential to encourage 3D awareness. Final prediction of the discriminator is given by this, wherein we just normalize the embedding function which operates on the camera target pose, and then there is a discriminator, and discriminator operates on the desired image which is obtained from after the differentiable rendering stage. And this log p, the probability is that the image target image from the camera pose v target which is provided is real. Now, once all the three blocks are completed, we need to train the model. The trainable components of the GMPI are all the networks which we highlighted throughout the slides. Then the weights initialization. So weights are initialized from the officially released StyleGAN V2 checkpoints, which is publicly available. Then the loss. The training loss consists of non-saturating GAN loss with R1 penalties. So this is the R1 penalties. The function is the log of 1 plus exponential minus x, and I refers to the real images, and V target is the observer's pose information. Now, the final step is the experiments. Now, this is the interesting stage here, just to see how even if just to check whether the generative multiplane image style representation even works properly or not. So first of all, some evaluation metrics based on which the authors have compared their results. First is the 2D GAN metrics. So in there, they have FID and KID, freshet inception distance and kernel inception distance. They should be lower the better. Both are lower the better. So freshet inception distance is just the Wasserstein 2 distance between multivariate Gaussians fitted to data embedded into feature space. And KID, it measures the dissimilarities between two probability distributions using samples drawn independently from each distribution. Then there is this identity similarity, which should be as high as possible. And then the depth and the pose accuracy, which are the geometric features. So these both should be as low as possible. So it makes sense, it is intuitive that MSE error should be as low as possible. So MSE error between the rendered depth and the pseudo ground truth should be as low as possible. And for the pose, it's again an MSE error. So these are the evaluation metrics. Now let us go to the results. The first result is the quantitative evaluation results. So they have considered basically 3 data sets, but here they have mentioned only the results for 2 data sets. So we see that, first of all, I should mention that GMPI is significantly faster, which they have also pointed out in their paper, than other models. And it is being able to be trained in a matter of 3 to 10 hours. Whereas the other state-of-the-art models like Giraffe or PyGAN or lifted GAN, they may take up to 2 to 3 days for training. We see that the GMPI outperforms Giraffe, PyGAN, lifted GAN, and Gram on the FID score. So you see FID should be as low as possible. So for GMPI, it outperforms all these methods. And based on these KID and FID metrics, while outperforming style SDF on only FID. And then GMPI demonstrate better identity similarity than Giraffe or PyGAN or lifted GAN. It also outperforms Giraffe in terms of depth. So we can see depth is less than Giraffe, so it is better than that. So it performs best among all the baselines on pose accuracy. So we can see pose accuracy is the best. So it's as low as possible among all these compared results. So overall, GMPI demonstrates that it is a flexible architecture which achieves 3D awareness with quite significant savings in the part of training. Then there are some ablation studies. So the effect of various design choices are shown in these ablation studies. So the authors selectively drop out 3 different parameters. First is the discriminator condition in the pose, then the plane specific features and the shading. So we'll see point by point how different cases affect the final results. First one is the base case. So it's not truly a 3D aware case, because it is quite clear from the depth and the pose score, it's extremely high. So whereas it produces quite acceptable 2D GAN metrics. But then we see the B part, which is again similar to the baseline condition, just that the generator uses only one feature without being trained on pose condition discriminator, plane specific features, or a shading loss. Thus, it is kind of similar to the results obtained in A. Now, the major changes start coming when we see from this C part and onwards. In the C sub, we see that DPC is included. DPC is the discriminator conditioned on the pose. So it performs well on the depth and the pose, but fails to produce realistic structures in the alpha map. So we can see as soon as we include this DPC, the depth and the pose scores have dropped. This is what is desired. In the D part, we get rid of DPC, but we include the plane specific features. So geometry related metrics, again, we can see that it performs very poorly. So in the absence of DPC, the GAN doesn't perform well in geometry related metrics, which is the depth and the pose, which is what makes the GAN 3D aware. Then there is this E part. So we have the DPC and the plane specific features also. So this produces good metrics on the depth and the pose. However, the KID and FID as well as ID values are generally worse than their than non-3D aware generators. We have this, when we see for E, we can see this figure also here. We see that depth and the pose are still very less, but we see this kind of concavity in the forehead, which is generated here. So this is attributed to the fact that we haven't added any shading in this case. So this is the E part. So that's why these kind of artifacts are obtained. But as soon as we add shading also in the F part, we can see that without any harm, without incurring any harm to our already good scores for the depth and pose, we can get rid of this concavity here. So this is what they have shown, that shading also, adding shading into the network is also something which which sometimes can be useful. So these are the ablation studies which they have run. So finally, we can see that GMPIs perform extremely well, given that they take extremely less time to train. So we can say that authors have developed the kind of method which in future can be developed furthermore, and which will be much more efficient in all the other parameters as well. So thank you. If you have any questions, I'm open.